Calc 2, Lecture 12. So we last talked about linear and quadratic approximations, and we defined, the linear approximation as L of x equals don't get to that right, equals f of a plus f prime of a times x minus a. And we talked about why that was true. We also talked about how a quadratic approximation can give us a little bit better at f of a plus f prime of a times x minus a plus f double prime of a all over 2 times x minus a quantity squared. Now, we can keep going further and further and further and call it whatever we want to in terms of, a cubic approximation and so forth. But we have a better notation for us, and that's called a Taylor polynomial. And Taylor polynomials are approximations. And basically what we're going to say here is that instead of calling this L of x, we'll call this P1 of x and this P2 of x. And the number over down here, for example, this means it is a Taylor approximation. It's a Taylor polynomial, which just means it's an approximation. Taylor polynomial of degree, this one would be degree 2, and it is centered at x equals a. Exactly. And of course, we learned that centering at x equals a means that f of a is equal to P2 of a, and f of b, I don't know why I'm doing that, f prime of a equals P prime 2 of a, and f double prime of a equals P double prime sub 2 of a, that they share all those. And if we go to degree 3, they would share the same third derivative at a, the degree 4, the same fourth derivative at that point.
Generally, when we do Taylor polynomials, what would be the highest degree we're going to be asked?
4? Well, as we could go more, I could say the first 4 non-zero terms. Okay, so that would probably be the rest. But those are type of problems where we're going to be manipulating known Maclaurin series, which we'll get to in next week. And we also have a name that when we want to center it, so if we want to center at x equals 0 specifically, okay, so we're talking about centering at x equals 0 specifically, such that, again, f of 0 equals p sub n of 0, f prime of 0 equals p n prime of 0, and so forth until they share all the same ones. We call this a Maclaurin series. Polynomial, because we're not talking about series yet. And so when you hear Maclaurin, all that means is that, or you read it, all that means it's just a Taylor polynomial specifically centered at x equals 0. Because if I give you a Taylor, I need to tell you where you're centering at. Where are you making that initial value of where they are, what you know the calculation to be? Okay, if it was a linear of degree 1, where is that tangent line being created at? That's where we're talking about centering. If I don't say that, then most likely I'm telling you it's a Maclaurin series, and therefore automatically it's centered at x equals 0. All right. So in that sense, for example, P1 of x would equal f of 0 plus f prime of 0 times x. P2 would be f of 0 plus f prime of 0 x plus f prime, double prime of 0 over 2 times x squared. So it's the same thing, just to note that when you hear Maclaurin. Next week, we're going to be going in terms of manipulation of infinite series, of known Maclaurin series. And so that's going to be a very important piece. So it's all fine and dandy so far. We talked about degree 1 and we talked about degree 2. But what about if you wanted to go degree 3 or further? And I know most of you have seen this, or you have the idea of what's going to happen. But I want to, once again, kind of show you the math that is occurring behind it. And so let's look at a degree 3. All right, so from our understanding here, then P3 of x is equal to C0 plus C1 x minus a plus C2 x minus a quantity squared plus C3 x minus a quantity cubed. I'm not going to go too far. We already understand that C0 is going to be the same thing, so it's going to be f of a. C1 is going to be equal to f prime of a. C2 is going to be equal to f double prime of a over 2. It's just an extension of the linear, or in this case, an extension of the quadratic going off to another term. All that math is going to be the same. No need to repeat that math. So now, though, let's look at, we know, to get the last one, we know that P3 triple prime of a must equal f triple prime of a. So if this must be true, we need to figure out what is going to be the value of C3 that makes this true. So just like we kind of did here, if I was finding P prime 3 of x, I would get C1 plus 2C2 x minus a plus 3C3 x minus a squared. P3 double prime of x would give me 2C2 plus 3 times 2 times x minus a. Oh, sorry, C3. And the reason why I'm specifically writing as 3 times 2, which I do know is 6, but the idea here is that we can kind of see a pattern that will arise. And what we get here, wait a minute, what happened here? Oh, okay. And P3 triple prime of x would equal, so 3 times 2 is also known as? 3 factorial, okay? Times C3. And once again, we know this is equal to f triple prime of a. So C3 is equal to the third derivative at a over 3 factorial. And in fact, C2 is actually f double prime of a over 2 factorial. But 2 factorial is just 2. Now, for those of you wondering, or maybe it's been a while since you did factorials, 0 factorial is just equal to 1. How many different ways can you group nothing together? One way. 1 factorial, how many different ways can you group one thing together? Also 1. 2 factorial, you can just do it 2 times. 3 factorial, 3 times 2, which is 3 times 2, which is 6. And technically, you're multiplying times 1, and 4 factorial will be 4 times 3 times 2 times 1. So what did we learn here? That P3 of x would equal f of a plus f prime of a, x minus a, plus f double prime of a over 2 factorial, x minus a squared, plus f triple prime of a over 3 factorial times x minus a cubed.
So when you said that you might ask for the first couple non-zero terms, that would be when f of a is 0 in a function?
It wouldn't be in a problem like this. And I might just ask you for the first 3 or first 4 terms and a general term type of stuff. It's when we go with the known Maclaurin series that we're going that's like I said next week, where I'll say the non-zero term, because it's much more faster process. Whereas this one makes you take the derivatives and all those type of things. So it's going to be a lot of work, and so I can't really make you go too far
Yeah.
on those ones. So we can use this pattern to actually create a formula for the nth term polynomial, nth degree Taylor polynomial, which is going to give me, f of a plus f prime of a, x minus a, plus f double prime of a over 2 factorial x minus a quantity squared plus dot, 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 plus the nth derivative at a over n factorial times x minus a to the nth power. Bless you. So we just continue that pattern depending on what degree of Taylor polynomial that we are looking for. Degree 4, degree 5, we can keep going out and more calculations. Of course, this can be computationally heavy for a lot of, because again, you have to find f, the fifth derivative at a, you need to find the fifth derivative of x. So if that's an ugly derivative or work, you have quite a bit of work to do. It also understands that you have known values, or you have a known function to work with this, right? So you had to know what f of x is, or know what those rates or values are, which is not always possible. And that's why in the next part, some of you were bringing up the question about why always Euler or this. I'm trying to give you that idea here. This is a better accuracy. It has far great accuracy, and each time you go a degree higher, your confidence in the accuracy it should be growing. It does not mean that by adding another term, your approximation will be more accurate. It will not be closer, that there will be a smaller error, because the function could just all of a sudden swing in terms of another direction, and all of a sudden yours goes off. And so initially, if you're doing a linear, it might end up almost being the exact value just by coincidence versus the other one. So it doesn't mean you will, but you should be more confident. And as we're going to talk about very closely, we can actually calculate how accurate we are in terms of what is the worst case scenario, and that's what happens in the real world. We write this as Pn of x equals the summation from n equals 0 to n of f of, oh, sorry, that's not an n equals 0 on the bottom. That should be a k equals 0. Sorry about that. K equals 0 of f to the k, the kth derivative at a over k factorial times x minus a to the kth power. And if you, for example, if you're doing 0, that's the 0th derivative means just the function value. So the 0th derivative is just f of a over 0 factorial, which is 1. So you get just f of a times x minus a to the 0, which is 1. So you just get f of a when you plug in 0. When you plug in 1 plus, when you plug in 1, you get the first derivative at a over 1 factorial, 1, times x minus a to the first power, which is the linear approximation, when you add, and so forth and so forth. Okay. There's little examples of how this works through, okay? So, for example, let's find the third degree Maclaurin polynomial of f of x equals the natural log of x plus 1. Now again, I've said Maclaurin, so that means we know it's just a Taylor polynomial centered at x equals 0. Okay, which does exist. We can find that. We know what the natural log of of 1 is, 0 plus 1, which is the natural log of 1. It has to be some value that you can evaluate and calculate. We already know we need to find all the functions. We already have f of x, so let's find all the derivatives up into the third degree. F prime of x would be 1 over x plus 1. F double prime of x would be x plus 1 quantity squared. And the third derivative would be positive, because a negative 2, and then a negative 2 times negative 1 gives me a positive 2 over x plus 1 quantity to the third. It would alternate positive, negative in terms of after that first term. All right, so what is f of 0? That's the natural log of 1, which is 0. What is f prime of 0? That would be 1 over 0 plus 1, which is 1. F double prime of 0?
Would it be -1 for the? Oh, F prime, not double.
Yeah. F double prime is -1. And the third derivative at 0 would be 2. So therefore, the third degree Taylor polynomial would be 0 plus 1 times x minus 1 over 2 factorial x squared plus 2 over 3 factorial x cubed, which of course we would clean up to be that P3 of x is equal to x minus 1/2 x squared plus, and now 3 factorial, and I know this is, we can do the math here and actually factor out, but 3 factorial is the same thing as what? 3 times 2 factorial, or 2, 3 times 2. That method, there's some work that you're going to need to be doing to understand that you can always break down a factorial to a smaller factorial. So 5 factorial is the same thing as 5 times 4 times 3 factorial, wherever you want to stop, okay? Little trick there. But yeah, we're going to get 1/3 here. X cubed. And then I could ask you to actually approximate, so, what is the natural log of 1.1 approximation? What is that value? I can ask you to do that by plugging it in. You can give me fractions or a decimal formatted a version of it. It should be something that could be relatively, that you should be able to do without the use of a calculator. I can also ask you for what is the error of the Taylor polynomial. So the error would be, actually we'll just do that. So let's do it. Let's make this question A. We'll do B. We're going to find, we're going to approximate the natural log of 1.1. Okay, so that means that we are plugging in, we're going to find P3 of what? No. 0.1. Okay, the natural log of 1.1 is approximately P3 of 0.1, because remember it's x plus 1. Because it's centered at 0, not centered at 1. If we were centering, it's because the function is natural log of x plus 1. That's the reason why. So that we could center it, and so the delta between our known value 1 and our approximating value 1.1 is 0.1. That's our delta x. And that delta x, or that change, is going to become very important. So how far are we going off in our approximation? 0.1. In this format, by doing it this version, we know that this is how far we are extending from where we're centered at. And that's going to have some application in our next piece. So this is going to give me 0.1 minus 1/2 0.1 squared plus 1/3 0.1 cubed. And that's just squaring the 0.1s. That's not too much of a math to worry too much about. So what is that? That's going to be 0.1 minus 0.01 and half of that, so 0.005, right? Plus 0.003. or 1/3. So it's a repeating, yes, 0. So it's, what is that, 3, 3, 3, 3, 3? Which, I mean, at this point, I'm going to go to the calculator here. 0.1 minus 0.005 plus 0.000333, which is going to give me 0.095333. You can go more. So that's what our approximation is. Find the error. And the error is defined, so the error in a Taylor polynomial is defined as the absolute value of f of b minus, or, you know, whatever the value is, minus the Taylor polynomial at, I want to be careful here. I'm going to do f of c here, a Pn of b. Basically, this right here just means it's the exact value. This is the exact value. Would it be the same one? F of, actually, it would be the same thing, right? F of b, sorry about that. It's the absolute value. The errors are always positive, just something to note. And so with this one, this would be something that we are going to use our calculator for. And so I want to find what is the natural log of 1.1. So this gives me, so it's the natural log of 1.1 minus P3 of 0.1, the absolute value of that, which is going to give me, I'm just going to do the math here, minus 0.095333, which gives me 0.00198. That's good enough. And so that's how much our function is, this is how much our approximation is actually off by. Yes?
So why did we do P3 or 0.1?
Because the function was as x plus 1. If it was just like x in there, if it was just the natural log of x, then it would have been 1.1 that we would have plugged in, because we were centering it at that case where we're going to center it at x equals 1. We decided to center it at x equals 0, so in order to center it at x equals 0, we shifted it off to x plus 1 for our function. All right? How are we out there?
Is that all for error?
That's the error, yes. Yes.
So if it was centered at, like, let's say x equals 1,
Mm-hmm.
then would it be like just kind of 1?
So yes, it would be 1.1, but it would also be, every term would have been x minus a, x minus 1, x minus 1 squared, x minus 1 cubed. Which ends up, when you plug them in, it ends up giving you the exact same thing afterwards. So it just, you know, so oftentimes when we center at x equals 0, it's a shifting, basically you're just doing a horizontal shift of where you would center it, and so you're kind of creating a new function that makes all the calculations a little bit more easier to handle. Plus, you can see how much your delta is off, how much your delta x is from where you're centering it versus where you are approximating, or where you want the approximation. But it's the same function, you're just literally taking it and shifting it to the left, however many units, if we're going from 1 to 0, if we're going 2 to 0, and so forth. I guess you could center at x equals -3, and it'd be a shift to the other one. So you're trying to like shift it towards the y-axis, is your value that you know that you can evaluate at x equals 0, and then shifting over, and then approximating. But it's the same work. All right, we're going to get to question D right now, but question D, we have to learn something now called the Lagrange remainder. Okay. So the Lagrange remainder, and so is basically, I want to make sure I did. So the Lagrange remainder of degree n of x is an absolute value. The absolute value of the Lagrange remainder is the error, which would be the true error, which of course is equal to, and we're going to write as, instead of the point at a, f of x minus Pn of x, absolute value. Okay, for wherever the value that we're trying to approximate at, that would be your x, and whatever degree that we have. This right here is the Lagrange remainder.
So that's what we just did.
Yes and no. Because we actually plugged in the value, which is different. Okay?
So this is just in terms of x.
And well, I'm going to prove to you the form of the Lagrange remainder, and that's why we're writing it here, because we haven't actually done it. We're going to prove of what the Lagrange actual remainder is. So hold with me. So if this is true, then Rn of x would equal f of x minus Pn of x, which means that f of x is equal to Pn of x minus Rn of x. And basically what happens here is the which, plus, yes. So it is, so what happens here is that this part just becomes the next term. The next term of the Taylor polynomial. Because it's what's hanging off that's left over, right? Because so what is left over is that next term from the two values. And so R, the Lagrange remainder, is stated as the nth plus 1 derivative and we're just going to use a different letter here, z, over n plus 1 factorial times x minus a to the n plus 1. And I know you have those questions, and I'm going to answer them right now. Why z? So the reason why it's z is it's not necessarily the next term, but the idea being that there is, and it technically comes from some mean value theorem ideas and concepts, that the next derivative, there must be some value z that would perfectly give us the rest of the remainder, because there must exist a value where the difference in the derivative at that point z, where z is between the values of where, between that delta x, where we're centering it and where we're trying to approximate it out to. Yes?
What happened to our absolute value?
It's just we're just treating it in terms of if it was positive versus or if it was negative. It's just some type of error, and therefore, this could turn out to be negative as well. Well, we're trying to find that. So then, so we're going to get to the maximum. So, again, what we're visualizing here, and I'll try to get it down. So we have some function y equals f of x, and we are looking at what this function is going to do at some value a, and we want to approximate it out to some value c right here. Basically, if we were going to do the linear approximation and we were trying to, basically get you all the way out there, sorry, I didn't mean to, and then, let's say that this was doing something like this. It was like a cubic. This value right here is where we're off by. That's our error right here. But if I were to add one more degree to it at some value z, it would have taken me directly over to that point right in there. I would have adjusted the rate one more degree, and at some value z between, and again, I don't want to get too much into it, but it's based on the idea of the mean value theorem working. So, but that is the Lagrange remainder. And what we're working on in this Lagrange remainder is basically this term is telling me there's this, the error is somewhere within here. And it's using the values of the next degree to kind of compensate for where it's going to be at. So wherever we take that value, it's going to change the rate at that value to get me down to that value of c, such that the two would have been equal to each other. I'll show you a quick. And let me simplify the image here. So, if let's say that this was our function, y equals f of x, and we wanted this value a right here, and we wanted to do some value c right here, and we wanted to approximate this as a degree 0, which is just going to be a horizontal line. We can see that this is going to be off by quite a bit, right? And so the question is, what is the worst that this could be off by? And in that case, we want to look at z is, when we're taking the value z, we're using z as its rate of this function. And the rate, the next degree would be slope, right? F prime. So basically, on this interval from A, and that should have been a B right there, sorry. From A to B, what is the maximum value of that next value that would give us what the slope was? So there's some slope in here, right? There's some value that if I would have adjusted it, it would have given me directly there, and then therefore that would have been right here, and there's the value of z that's going to be working in there. Once again, it's the mean value theorem at work. And this is simplifying it in terms of degrees 0 and 1, which is something that we can visually see, but the math is still there for the other ones, of course, adjusting for factorials in there. Now, what we want to know is basically, so there is some value that will do it, but in this, what is the worst case scenario? For f prime, for f prime of z. Since this is a Taylor polynomial of degree 0, right? The next one will be the first derivative. So what is that worst case scenario? That's what we can calculate. That's what we can figure out. We can figure out what is the worst case scenario versus what is the exact value that would give it to me. We don't want to figure out what is the exact value that would give me the right answer, because the truth is, in application, we actually never know what the actual value of f of b is going to actually be. That's the purpose of here. We don't know it, or we can't figure out what the actual value is. In practice, and when you're trying to actually do this in the real world, in NASA, wherever it is, this is the idea. So what we can do is we can ask ourselves, okay, what is the worst, over that interval from where we know to where we want, what is the worst case of the next rate of change of the next derivative, of whatever degree that we're going off to? And this is known as the maximum Lagrange error. Okay, the max Lagrange error, which is equal to the maximum. We're going to do a EVT problem, extreme value theorem problem, of the absolute value of the Lagrange remainder, f of n plus 1, the n plus 1 derivative at z over n plus 1 factorial times basically the delta x, how far is it that we want to be going? B minus A.
Is that the absolute values?
Yeah, sorry. Oh, yeah, I was doing C. What is that? F to the n plus 1. It's the next derivative of the B minus A to the n plus 1 close the value. Basically, this right here is that delta x of how far you are trying to reach your approximation to where you want to approximate it from where you know to where you want. How, and we said for small values of delta x, it is accurate. And the question came up last week, our last lecture, how small is small? Well, this is going to basically tell you, as it gets bigger, it's going to give you an actual value of how far we can be off by. Now, this is a maximum where the function is a z. So we're using the variable z as our derivative, which just basically means that this is a maximum problem of the absolute value of the nth plus 1 derivative of z times the absolute value of b minus a to the n plus 1 over n plus 1 factorial. What I'm saying that this is a constant. And this is what you're trying to do the extreme value theorem problem on. We're trying to find the maximum of this function in terms of z, and that's just change the variable so that we're not using the x and we can understand what it is. And what is it? And that z value that we find where it is, that's the c point. That's where that maximum occurs within the interval, or that's the z that we're between a and b. And so basically you're looking at from the interval a to b. It's an extreme value theorem problem on that interval for that right there. So looking at that example for D, what is the max Lagrange error for f of x equals natural log x plus 1 of the third degree Maclaurin to approximate the natural log of 1.1, or f to approximate f of 0.1, which is the natural log of 1.1. So how much are we going to be off by? What is the maximum value that we're going to be off by? All right. This is what becomes very important in the real world when you can't actually figure out the actual calculations of what it's going to be. Sometimes it's just important to know, and this is what happens in a lot of different things, like sending something to the moon or sending a rocket to outer space. You can't figure out what the actual solution is, but you want to make sure that it's within a margin of error, that it's no bigger than the difference of how much it's off by, no more than 0.000001. And you want to make sure, because as long as it's within that error, you're going to be able to land the ship, right? And it's not going to fly off in terms of, forever and ever and ever and not hit your destination. So as long as we reach there, and the same thing happens with type of anything that you're trying to build in buildings. Most likely you can do more calculations, but if you can't have something that you can actually calculate, but you can approximate it, then you can make sure that your solution is within that the whole building's not going to collapse type of strength, those type of things. So to do that, we want to find the fourth derivative. So we want to find R3 of x is going to equal the fourth derivative of z over 4 factorial times x minus 4 to the n plus 1. Or sorry, to the 4th. X minus this is going to be 0.1 to the 4th. Yes? Then again, this is your delta x. This is your b minus a. This becomes your b minus a value. That's your delta x, how far you're going to be going off from there. You're using it in that formula. Because it's basically saying, this is the worst case scenario. This is the worst case. And if we think about over here, how far am I going off by that? So what's the worst case slope, and how far am I going with that slope? And that's the worst it's going to be off by if I utilize that from the beginning. All right, which is equal to, well, the fourth derivative, which we never found, the fourth derivative would be what? Negative 6? So f4 of x would have been negative 6 over x plus 1 to the fourth power. Okay. So it equals negative 6 over 4 factorial x plus 1 to the fourth times 0.1 to the fourth. Good? Which means now to find the maximum Lagrange, bound error. Should have used that word bound in there because it's bounded by the interval a to b, which in this case is the interval 0 to 0.1. Okay. Then we need to maximize the absolute value of negative 1 over x plus 1 to the fourth, basically. And I'm going to do that part, and then everything else is just a constant. I'm going to ignore everything out. Technically, I'm maximizing the entirety, but all I really want to care about maximizing is this piece right here, which is the same thing as maximizing, or I should change that to a z. Sorry, just to be in the form. If you put it in x, it really doesn't matter much. The absolute value are 1 over z plus 1, because the absolute value is not going to matter to the fourth power. Now, the reason I can get rid of that absolute value is because over that interval, it's never going to equal, it's never going to be negative or positive. If it was negative versus positive, then you do run into an issue where the critical point could happen right in the center, but we know if that's the case, then it's going to be 0 at that point. It is possible, where this minimum happens or where this maximum happens can happen anywhere along the interval. You have to do an EVT problem, and that's going to happen on your p-set. It's not going to be at the endpoints. But this function right here, z equals, what is this function always doing? 1 over z plus 1 to the fourth f of z, or h of z, I'll just put it as this function, h of z. This function is always doing what? As z gets bigger and bigger and bigger, what is happening? Yeah, it's always decreasing. This just makes my EVT problem a little bit easier. So since it's always decreasing on the interval, that means that the maximum is at where?
The highest value.
Oh yeah, it's always at the highest value. But since this function is always decreasing along the interval 0 to 0.1, at 0. The left bound. Because it was always decreasing. If this function was always increasing, then it would happen at the right endpoint. Okay? Does that make sense? So it just depends on, if the function is not always increasing and not always decreasing, then you need to take the derivative of f prime of z, which would be the next derivative, which in this case would be like the fifth derivative, and you'd have to set that equal to 0 like an EVT problem. Because basically, this is the function that you are trying to maximize. How do you maximize a function? Well, EVT says that you take the derivative of this function, set it equal to 0, then you plug back into this original function the critical points and the endpoints. And whatever gives you the maximum value, or the absolute value, maximum value, that's where it occurs. But since this function was always positive anyways, or always negative in this case, we didn't really care about what that value was going to be. But you may need this in some problems. Just it doesn't really matter in here. So it happens at x equals 0. So that means the maximum Lagrange bound, so the maximum Lagrange bound error is equal to, let me actually find that value, sorry. So h of z, h of 0, sorry, would equal, well, just in this case, 1 over 1, right? 1 over 0 plus 1 to the 4th, which is just 1. Yes?
Wait, why would it not be z equals 0.1? Because if you have like 1 over 1.1 to the 4th, wouldn't that be less than 1?
If you plug in 0.1, you're going to get a smaller value. If you plug in 0.1 into this, your value gets smaller.
Well, 0.1 for z, right?
Yeah.
So it'd be 1.1 on the bottom, which is like...
Yeah, so it'll be 1 divided by 1.1 to the 4th power, which is going to be a smaller value than 1 over 1.
I'm thinking of it reversed.
Yeah, so that's it. That's right. So, and this one's a nice simplification. We just get 1. So then that means that the maximum value is going to be, in this case, 1, or, you know, we can put the 1 times all those leftover terms, or basically, you know, if I put this as 1 over right here, right, it's negative 6. Let me just write it on the next line. Negative 6 over, or sorry, it's 1 times the absolute value, and I put in the 6 already, so 6 over 4 factorial times 0.1 to the 4th. Which if I plug this into my calculator, 6 divided by 4, 6 divided by 4, math, number, factorial, times 0.1 to the 4th power, gives me 0.000025. And if we look back to our previous answer, whoa, why did we get something different? What is off? I got to double check something in terms of the math, which I'll do right after the break. I try to do a different example here, and it's throwing me off because I don't have the final answer in here. So I will fix this answer. This value right here, and something went off by it, I got to double check it. That's what I should never try to add a new problem. This wasn't, I haven't done a Lagrange for a while, but we've been doing it at a good pace that I wanted to add it. Something happened where this value up here should have been less than that value. So this, and I was looking at this value, this seems a little bit more accurate than I thought it should be. I think I made an error on this value right here when I did this calculation. So let me just double check this calculation right here. Basically, this value should be less than this value because it's saying that this value should be off by at most this much right here. So I got to just figure out where that math did. I'll do that over break. It's 11:31. We'll break to 11:36, and I'll fix that issue during that time. All right, so the issue that I had from behind was when I found the actual error using the calculator, I did the calculator bad. This was the actual error, 0.000231535. So I was like, man, that seems too small of an error for going for 3 degrees, third degree. So yeah, that value was what was wrong here. And as we can see, the actual error must be less than the maximum Lagrange bound error. And it'll always say that. And what that means here, and the purpose of here is that we don't actually ever know the actual error. This is basically in practice, this is unknown. In practice, in application, the actual error is unknown, but we can calculate the Lagrange bound error, and we can say that, oh, I got an error of a maximum Lagrange error 0.00025, so I know that my error, the actual error, is going to be something less than that. That's the worst that it's going to be off by. And if that is reasonable to work with and continue with, and I know that this error, and this is how much it's going to be off by, is within my margin of error and reason, then I can continue. And if it's not, then there's a scenario where it's more than it reaches if that wasn't, and I need it to be within like 0.0002, then I'd be like, oh, that doesn't work because there's a possibility that, everything might just fold and all that stuff. So I might have to go an extra degree and so forth. So that's what the Lagrange bound error is. You'll always, and you've done it right, like I had just seen in my lecture, and apologies for that, that this actual error will always be more than the maximum error. All right? Questions there? All right. Now, computational, so Taylor is very accurate. Let me actually shift that over. Is very accurate, but is computationally heavy. And it also higher order differential equations. And that's not typically within what we have. And so you need, and when I say higher order differential equation, that means you need to know the rates and the rates of the rates and the rates of the rates of the rates and all those type of things that's going to go on there. So how many degrees are you going on there? Once you take the course, many of you will take the course 1803, differential equations. You have an entire course that's going to be on this idea of differential equations. The most one is we often just work with a first order differential equation. And so, when we want to work with something that, typically we only know f of a and f prime of a, then basically your only option would be a degree of Taylor polynomial of degree 1. And we kind of know that a Taylor degree of polynomial of degree 1 is not going to be very accurate in terms of that. And especially when we're stepping out, the further we step out, like a whole 1 unit away versus like a 0.1, even 0.1 can seem kind of far, it might give us an error that is kind of unacceptable, right? And in the real world, I think many of you have seen the movie Hidden Figures. This is basically what they do and use in terms of, they use Euler's method in that movie. It's where the main character comes up as a solution. Basically, the position of the space shuttle that's coming in, and the thrusters, which is going to be you're changing your rate of change. And so based on that, that's going to create a new line of movement, and then the thrusters will a new line, and you're able to get to where you want to be, or approximate where you want to be, using just the position and the rate of change, the first derivative value. So as such, we have what's known as Euler's method, not Euler's, it's Euler's method, which is an advanced step method of linear approximation. For f of b given a f of a and known derivative. In other words, you know how changing it at the different points is going to affect your rate. And actually, I'm just going to jump this off onto the next page. Okay. Visually, let's say this is our function, y equals f of x. We know this value here. This is where we initially start. And therefore, in a typical problem, we make a tangent line at this point. And we want to approximate the value here at b. Well, this tangent line, that difference in here, that error is going to be quite off for going 1 degree. So instead of That's just doing it in one step. But what happens if we just wanted to break this down into 2 steps? So we want to find halfway between. So this whole piece right in here is your delta x, but what happens if we just go delta x over 2 and then use another delta x over 2 to go forward? And so basically what's going to happen is we're going to get to this point right in here on our function, on our tangent line. We're going to move along our tangent line till we get to the halfway point right there. And then I'm going to use the tangent lines, the slope at that tangent line, to reposition, let's say it's going like this, to reposition a new tangent line that's going to go the rest of the distance using the rate at and the current value that we are at that point, what would be the slope of that value function. And so we are able to reposition our tangent line. And so we, in essence, have 2 tangent lines that go right in here. We use a tangent line, then we reevaluate the equation of our tangent line, and we move on from there for the rest of the distance. And this would be right here. This is a 2-step. We can go 3, 4, 5, 6, 7, 8, 9, 10, however many steps we want to. And this is going to be less computationally heavy on our work. Now, of course, there is some issues in regards to, of course, the Taylor polynomial is more accurate, but sometimes we don't have the information available to us. So Euler's method, using n steps, gives us a delta x of b minus a over n. We are going to start at x comma y, which is in this issue, this is our a, where we're starting right here at a, and we're going to go at f of a. And we want to figure out where it is at our new point, b minus, or at that other value. The first step, or remember, we know that delta y is going to be dy dx evaluated at that point, x comma y, times delta x. This is from earlier when we did that linear approximation piece. Basically, we're taking the slope and we're multiplying the slope by how far we're going to step out. And that'll give us where we are on a new point in our line. So in our first step, after our first step, once we complete our first step, we will now be at the point x plus delta x, right? We moved across delta x, which is the b minus a over n. And our y value will be now y plus delta y. In other words, this point right in here is now a plus delta x. I meant to change the color. And this point right here is now f of a plus delta y. And then we repeat. We repeat until we reach x equals b. Until we've reached however many steps I've requested. And you'll know this is the same thing. If you're doing, it's going to be explicitly told 5 steps. So you know you're going to do it 5 steps, and you'll always end at that value that you want it to. So if you're going from 0 to 4, and I say go 8 steps, and each step is going to be 0.5, 0.5, 0.5, and once you get to the last step, you'll finally be at that 2 or whatever the value is, 4. So the process, and many of you may have a different process, and if you've learned Euler's method, and you have a method that how you set it up can vary, and please stick with that way that you've learned with your teacher if that is the case. I like to set it up, my table, as here's my xy, then my dy dx, then my delta x, which will always be the same, my delta y, which of course is that dy dx times delta x, and then my new point x plus delta x, y plus delta x. Now, this delta x value, once again, this will always be b minus a over n, so that will be all the way down the same value for the delta x. And you have your starting point. So wherever your starting point is, you'll have it right in here. This is your starting point, a f of a. You'll find all this work by plugging a f of a into dy dx and doing it, and then you'll be at a plus your delta x, f of a plus delta y, and then you put that point right into your next, and you repeat the process and you go through it until you are done. However many steps you are taking. And we'll do an example right now, just as I get you to write this down. Again, if you've learned, you have different methods of how to organize it. I know some people don't even use a table or table organization like this, and you know, if you've learned it and practiced it a lot, you know, in high school you get like a week to do this. For us, you get 15 minutes to do this. So that's the big difference of your steps and orders. But I like this, and you know, and this layout right here is showing you your understanding of what Euler's method in the process is, rather than just some made up thing. Now, most likely 4 or 5 steps is the most that we have. Let's do an example and end the lecture. I know Abner wants that, right? dy dx equals x plus y. We know that f of 2 is equal to 0, and we want to use Euler's method. And it usually happens a lot more. You guys are not as tired as past year's classes, I'm saying. You guys think you're more tired, but you guys, there's usually you guys have done a very good job of your energy level. F of 3 with 5 steps. All right, since we're doing 5 steps, then my delta x is going to be equal to, I want to do 3, and what's where I want to approximate, 3 minus 2 over 5, which is going to give me 0.2 as my steps, my step length. So my xy, my dy dx, my delta x, my delta y, if you want to write what delta y is, and then your x plus delta x, comma, y plus delta y. Remember, delta y is just multiplying the 2 values. So we are starting at what point? 2, comma, 0. We plug x equals 2, y equals 0 into dy dx. So I'm plugging into here, this point. We get 2 plus 0, which is?
2.
Which is 2. Yes. Now also, how many, I'm going to actually fill this out. We know how many steps we're going. So first step, second step, third step, fourth step, fifth step. We also know that this is always 0.2, 0.2, 0.2, 0.2, 0.2. First step, second step, third step, fourth step, fifth step. We actually don't even need the bottom piece. Sorry, I went too far. And this is going to give me my final answer on that last one right there. My delta y is when I multiply these 2 values together, which gives us 0.4. 0.4. So now we're at 2.4, comma, or sorry, 2.2, and this next one will be 2.4, this one will be 2.6, 2.8, and then this one is going to be 3. That one's always going up by 0.2 for your x. And we now have a value of 0 plus 0.4, which gives us 0.4. Okay? Follow along. Did you follow that first step? Did you follow that first step? Then it's pretty straightforward. Delta x is always the same value that we calculated right in the beginning. Your b minus a. So that's why I say it's always going to be the same delta x. Delta y is where we multiply these two right here. So we're multiplying.
Okay.
Basically like this.
Is there ever a scenario where Euler's method uses different step lengths?
It just depends on how far you're going. So if you want to, we got from x equals 2 to x equals 3. If we're doing x equals 2 to x equals 4, if we're doing
No,
5
I mean,
steps.
like you do one step with 0.2 with delta x equals 0.2, and then you'll have the next.
Euler's method, I mean, you can do that, but the Euler's method is just like, it's kind of like a Riemann sum. Like, you can have different step lengths, but why put yourself through that?
Well, yeah, the problem.
Correct. And the idea is that you could technically do a Lagrange bound error 1 degree of each single one of them, or, you know, it's just keeping the same one. And then, so I'm going to run through the rest. So now we're at 2.2. This one will give us at 2.4. This one will give you at 2.6. This one's always going to give you 2.8. That's going to be, that's how we're always going to get to. And we're going to plug in our new values. So 0.4, 2.2, and plugging in 0.4 gives me 2.6. I'm just adding those two values together. Times 0.2 gives me 0.52. Adding these together, adding my y's together, my delta y's now gives me 0.92. All right, so now this is 0.92. Add these two numbers together because it's x plus y. That gives me 3.32. Multiplying that by 0.2 gives me 0.664. I'm just running through these values and the processes. Adding 0.92 plus 0.664 gives me 1.584. So now I'm at 1.584. I plug these back into my dy dx, which in this case means I'm just adding them together, which gives me my 4.184. I multiply this by 0.2 to find my dy, my delta y, which is going to give me 0.8368. I add this to my previous y value, which gives me 2.4208. So now I'm at 2.4208. I plug these two values back into my dy dx, which in this case is, again, adding them up. 5.2208 multiplying by 0.2 gives me 1.04416. Adding my delta y to my previous y gives me 3.46496. And therefore, f of 3 is approximately equal to 3.46496. And that is Euler's method. Now, I did a lot of steps there. Like, I'm not, 5 steps, and with these usually it's like a 2-step problem. Yeah, it is a final exam. I could go 4 steps. I'll make the numbers, 0.5, not super complicated and icky to multiply. You should be able to do it. The calculation should be there so that you can do it on when I test you on this. Okay.